Good morning, grade 12s. Well, actually, good afternoon. And I just wanted to. I didn't want to wait till Wednesday for you slackers to draw this graph, so I did it for you. Okay, because the next lesson and for this week we're going to be working on questions like this. So, I'm trying to keep it to whatever, a few hours per week total. Okay, so. Yeah, so this is the lesson for this week, okay? It's on Hooke's law. Now, Hooke's law has to do with linear springs. Now, what is a linear spring? A spring, okay, if you remember in the lab, I stretched out a spring by hanging masses onto it. And so the way it works is, as you stretch the spring out, it takes more and more force to stretch it out. Well, if you draw a graph, which is what I wanted you to do, of force versus stretch, then what you get is something that looks like this, okay? A straight line. And in fact, this is actually the data from the graph. It looks perfectly straight, maybe a little off where I circled over here. So, oops, I erased it. So where I circled here, maybe slight deviation, but otherwise that's perfect data. And the funny thing is, I mean, we collected it. You saw me collect it. I actually wrote down the actual values and it worked out very, very well. We got a straight line. Okay, now I asked you to measure the slope. So slope is just rise over run. I got 17.7 newtons per meter. Notice I converted the centimeters to meters. Now I didn't when I drew the graph, but when I found the slope, I did that to put it in standard units. Okay. All right. So Hooke's law. Hooke's law is basically the equation of this line. So it's a force versus stretch graph. And so let me tell you about Hooke's law for linear springs. Basically, by the way, anything elastic, like an elastic band, a hair elastic, or a spring, a bungee cord, whatever, they all behave like linear springs, which means the more you stretch them, the more force it takes to stretch them, right? So there's a relationship between force and stretch, and that is Hooke's law, okay? So this is the equation of that line. Now let me define these variables. K is what we call the spring constant. Now in our lab up here, that is K. Okay, so spring constant, and it's the slope of force on the spring versus x on the graph, right? And the units of K are newtons per meter. Okay, x is how much stretch you have in the spring. So if you like, in this graph here, this is x. Now it's on the x-axis, so makes sense. Okay. Anyway, that is the change in the natural length of the spring. So for example, if you had a spring that is naturally that long, and you stretch it, so now it's here. So this is like here, I'll stick with the rainbow color. So this is unstretched. Okay, and then you take that same spring and you stretch it. So the distance from here to here in the stretch spring, this distance here is x, okay? The amount that you've stretched it, say we've attached it to a wall or something. So you understand? X is the stretch. Now x could be also a compression because some springs you can compress, and the change in length would be like if it gets shorter, and the amount it gets shorter by is the compression in the spring. We'd still call that x, okay? So it's the change in the natural length of the spring. Okay, and this natural, unstretched, uncompressed length. All right, so an Fs, of course, is the force on the spring in newtons, I should say, okay? And that would also equal the force of the spring on the suspended mass because of Newton's third law. All right, so this, in a nutshell, this formula I'll put in a box, that's Hooke's law. That's it. Pretty straightforward, right? All right, so let me give you an example of how you might use this law in a problem. So down here, I'm going to write examples. Okay, and the examples go like this. Let's say we have an inclined plane. I'm going to make this a little bit harder than the one that we did in the lab. Let's say we attach the spring to it like this. And then what happens is we attach a little mass here. This little mass, okay, no friction. And we'll make our angle of inclination 30 degrees. Now what's happening is the mass has caused the springs to stretch that much. So that my rainbow is the same spring, there's not two springs there. But this, from here to here, is the amount of stretch from the natural length of the spring. This is the natural length of the spring over here where it's colored black. Okay? So that is the stretch in the spring. Now my question for you is, if this mass is 100 grams, and our K value of the spring, let's say students, we did this lab, we'll use the same spring. So our K value is 17.7 newtons per meter. Then my question for you is, how much will it stretch the spring? What's X? Okay, so let's go ahead. And how do you solve this one? Well, same way we solve everything else, pretty much. You draw a free body diagram. So there's gravity. It's an inclined plane, right? So there's gravity, there's a normal force, but there's also the spring, which is holding that object up. All right, now if I zoom in on this a little, if you remember how we did inclined planes before, we treated this as the x-axis, this as the y-axis, and gravity is off-axis, so it's got a component like that and a component like this, right? And 30 degrees fits in right here, okay? And we actually don't care about the y components in this problem because there's no friction, so we'll just look at the x components, okay? And you get max equals force on the spring minus force of gravity times the sine of 30, okay? Now let's go ahead. This one is 0 because there's no acceleration, so A equals 0, right, in this problem. And therefore, the force on the spring is equal to mg sine 30. Now here's where Hooke's law comes in. We're going to replace force on the spring with kx. So no problem at all. Now solve it for x. Okay, so 17.7x is equal to 0.1 times 9.8 times sine of 30. Okay, so I'll take out my calculator. 0.1 times 9.8 times 30 sine equals divided by 17.7. I get 0.0277. So 0.0277, yeah. So I get x is equal to, oops, 0.0277 meters. Now for reference, 100 grams placed on the spring in the lab straight down, stretched it more than that, of course. Okay, it stretched it by about 5 centimeters, but in this case, it's only going to stretch it by 2.77 centimeters, right? So just so you get sort of your scale, right? A fraction of a meter, but a meter is a lot, right? If you stretched it a meter, it would break it anyway. It can't stretch that much. Okay, but 2.77 centimeters, no problem. So there you go. There's your first spring problem. And notice that it's in equilibrium. Okay, so we gently lower this down. We didn't drop it. Dropping it is a very different problem. When you drop it, it does simple harmonic motion. It bounces up and down, right? And I'd like to talk to you about that problem next. Okay, so this is Hooke's law. This is how you do force problems where their objects are in equilibrium. Okay, so now, unfortunately for you, the story doesn't end there. There's more to it. So now let's look at energy. Okay, so here's the deal. I'm going to sketch this graph again. Actually, let's see if I can do this. Okay, there's my graph. Okay, there you go. It works. Actually, I'm going to make that a little... I'm going to stretch it. It's like a spring. I'm going to stretch that around. Move that down here. Okay, so there you go. Force versus stretch. There's my graph again. Now what I'm going to do is I'm going to ask you to recall work is equal to area under a force versus delta D graph. Well, this is a force versus distance graph, this force versus x. So this is Fs on this side, this is x down here, okay? And therefore is equal to the area under an Fs versus x graph. Okay, so how much work does it take to stretch a spring out? It does take work, right? You are applying force through a distance. Well, this area under here, so I want to stretch it out by 20 centimeters, or whatever, here. This area here equals the work done, and work is equal to the change in energy. So what happens when you're doing work on a spring? Well, the spring stores energy. It's really cool because it's got elastic potential. So this is a new kind of energy. We call it elastic potential energy. And anyone who has pulled back a rubber band and pointed it at someone else, and you say, all right, I'm going to point this at you, and then you see them flinch or whatever, it's like, you know what's going to happen if they let it go. If they let it go, it's going to turn into kinetic energy and it's going to be flying towards you, okay? So when you stretch on an elastic object, energy gets stored inside it, okay? And we call this elastic potential energy. All right, now, what's the formula for elastic potential energy? Well, it's very simple. If you look at this linear system that we have here, the energy stored in the spring is equal to the work done when you stretch the spring, which is equal to this area, the area under the line. So that's the area, well, all right, so that's half the base times the height, right? So the base is x, it's the stretch, okay? The height is the force on the spring, okay? And we're gonna use this formula that the force on the spring is kx, So therefore, the energy stored in the spring, actually let me move those dots. So therefore the energy stored in the spring is equal to 1/2 x times kx, or as it's written in your textbook, half kx squared. So this is the sort of second part of Hooke's law, okay? That the energy stored in the spring is half kx squared. Now k, of course, is the spring constant. It's the slope of that line, okay? So in our case, that spring constant was 17.7 newtons per meter. So that's what k is. X is the stretch, okay, and ES is the energy in the spring. In the spring. So that's Hooke's law. Okay, Hooke's law has two parts. So just to summarize, Hooke's law has two parts to it. It has an energy component, which is given by this equation in the box, and also has a force component, okay, which is given by F equals kx, right? It's given by this formula in the box right there. Okay, so just to summarize, okay, the elastic potential energy is that, and the force on the spring is kx. This is all you need now. These two things will cover whatever you need for springs in problems, okay? Now, for example number 2, I want to do the second part of the lab, okay? We drop something on a spring. You can do bungee cord questions like this, okay? The thing is, forces are extremely complicated when you do a bungee jump because as you stretch out that bungee cord, the force that it exerts on you is increasing with the stretch. And so it's non-variable force, or sorry, it's a variable force, okay? And it's stretching out our spring. And that variable force will have a non-uniform acceleration, okay, as the object is falling, as you're falling, okay? And then you reach a maximum stretch, but you don't stop there. So you're not in equilibrium, you're gonna accelerate back up. And that's what makes the bungee cord ride so much fun, right? All right, so let's just do, in our lab, we did this. Okay, so we dropped a mass of 250 grams. So let's take our spring, The spring is unstretched. And what we're going to do is we're going to take a 250 gram mass, and this spring has a K value of, that's our spring in our lab, right? Newton per meter. And then what we're going to do is drop it, okay? Now, this here, at this moment, at the time of the drop, X is 0. So the spring is not stretched. Doesn't mean it has 0 length. It has its natural length, which is not stretched or compressed, right? So there's no energy stored in it to start with, okay? Now it's dropped. Okay, now the question is, we know what's going to happen. We drop it, and I'm going to use the rainbow color. So the rainbow is going future in time, okay? We know it's going to fall. And then it's going to reach some other point down here. So this is what happens at sort of the bottom, okay? Now I'm going to ask several questions about this. We know that this is the amount of stretch, right? So it's going to stretch out by that much. But it's also equal to, I'm going to change color here, the height that the object falls through, okay? Now I'm going to ask the same question. What is that number, okay? Now, this question, because it was dropped, you do it very differently. Because what's happening is by dropping it, you're letting gravity do some work on it. If you lower it in your hand, then as we did in the lab, we just lowered it in part A of the lab, and then it reaches equilibrium. You're not letting gravity do the kind of work that gravity could have done otherwise, right? Because you're interfering with it with your hand. And so it finds an equilibrium point and just sits there, okay? But now if you drop it, and gravity is free to do its work, and there's more energy in the system, so that pushes it down lower. But then it's not in equilibrium, and it bounces up and down, as we saw in the second part of the lab. All right, so what you do is, at the top, this is not a free body diagram problem, okay? At the top, what kind of energy do you have? So here, the energy in the system. There's 3 kinds of energy now that I've introduced this to. There's kinetic, gravitational, and spring energy. So at the top, let's do a little table. There's EG, there's EK, and there's ES, okay? So here's my little table. At the top, these 2 are both 0. In other words, we didn't give it any speed, so it has no kinetic energy at the top. Remember that EK here, I'm just going to remind you that EK is 1/2 mv squared. EG is mgh. And ES, this is the new one today, is 1/2 of kx squared. So in order to have EK, you have to have speed. So at the beginning, there's no speed. At the top here, V is 0. And at the bottom, by the way, V is 0. Because those are the 2 points where it's not moving. At the top and the bottom. When you're on a bungee ride, you stretch out your maximum stretch. At the very bottom, for an instant, you come to rest, but you're not in equilibrium, so you're going to go back up. But for an instant, you're at rest. Okay. Now at the top, we do have EG at the top, right? And the EG is mgh. That's what we have at the top. Okay. Now, at the bottom, down here, so at the top is up here, right? At the bottom, what do we have? Well, do we have any EG? Well, we'll find out. EK and ES. So here, at the bottom, we can't go any lower. So this one's 0. This one's 0 too, because we have no speed at the bottom for an instant. But here, we have spring energy. Now, by the way, in case you're curious, I'm going to draw a little line here. Okay. In the middle, in the midpoint, as it's on its way down in this section here, what's happening is this one you're losing. Here, okay, so what happens is as the object falls, okay, it gains speed at first. Gains speed. Okay, so it gains kinetic energy and it gains spring energy as the spring stretches out. So what's happening is you're gaining in these two, okay, but losing in this one, okay, losing, okay, in that one as the object falls. So let's say you start off with $100, I'll use a money analogy, $100 of gravitational energy at the top. And then there's 3 friends sitting in on this ride, and the gravity guy has 100 at the top. The other 2 guys have nothing. Okay. What gravity does is he shares as you go down, he's going to give some to kinetic and some to spring energy. Okay. And then the kinetic will take some, but then when the kinetic reaches about the halfway mark, it starts to slow down. And then what's happening is the only one's gaining is the spring energy. So he hands it over to the spring. When you get to the bottom, the spring has all the money. But what the spring guy is going to do is he's going to give it back to the other 2 guys on the way back up. Okay. So anyway, it's kind of cool how it works. You're going to have to get a sense of a mechanical system like this. So it's a new type of mechanical energy, the spring energy thing. And here's the deal. The energy at the top must equal the energy everywhere, really, but at the bottom are the 2 points that we're interested in because we want the maximum stretch. So that's mgh will have to equal half kx squared. Okay, so here at the bottom, all the energy is spring energy. Here in the middle, you've got all 3 kinds of energy in the midsection. But at the top, you only have 1 kind of energy also. The only thing you have up there is Eg. So these 2 things have to be equal, top and bottom. Okay. Now, here's the deal. X and H are the same variable. The amount of stretch and the change in height are both the same thing. So I'm going to write mgx equals half kx squared. That's going to cancel with one of those. And I get, therefore, x will equal 2mg over k. Okay, now I will plug those numbers into a calculator. My mass is 0.25, so it's 0.25 times 9.8 times 2 equals 4.9 divided by 17.7. And I get about 27.7 27.7, here, let me do that again. Make sure I give me the right number. Yeah, 0.277. Okay. Now, in the lab, this is equal to 27.7 centimeters. Now, in our lab, I'm just going to write note. In our lab, in part B, I got x equals, when I dropped it like this, I got x equals 25.5 centimeters. I'm a bit off. Okay, I'm off by about 2.2 centimeters. Why is it off? Well, the reason is, what are we not accounting for in this system? We're not accounting for waste heat. There's always waste heat, right? So whenever energy changes forms, in this case going from gravity to the spring, you always get a little bit of loss. Okay, and that's why a bouncy ball doesn't bounce back up into your hand. That's why the spring doesn't stretch, it doesn't go quite back up to the top again on the second oscillation. It's the same thing. You're going to lose a little bit of energy on every sort of bounce that the spring makes. And so we lost a little bit, lost about, I don't know, 10%, okay, of the energy there. It's not an error. Did the lab correctly. The reason why it's not supposed to work out to give you exactly the perfect result. You're going to get some energy loss, okay? And so why not perfect? Whoops. The answer is waste heat. In other words, when we sort of proclaim that the energy at the top equals the energy at the bottom, we're saying there's no waste heat. Okay, but actually you're going to lose we can figure out how much waste heat there was in the system. In fact, that's one of the questions I'm going to make for your lab. But yeah, there was a little bit of waste heat there, so we lost some energy, and so it didn't stretch out as much. So anyway, that is how you do questions involving springs. Okay, now this will add a layer. Okay, I just want to put summary. This will add some level of difficulty to the problems you're going to solve. You'll see what I mean. Summary for mechanical energy problems. So problems involving conservation of energy, energy problems. There are 3 kinds of energy now, okay? 3 kinds of energy, okay, that could be in these systems. We're going to add a 3rd kind of energy that we never did before. So we have gravitational potential, mgh. We have kinetic energy, 1/2 mv squared. That's what we did in grade 11. And now we're going to add a 3rd kind of energy, spring energy, is 1/2 kx squared. Okay? And so that is a little summary of everything you need to know about springs. You're supposed to get that from the lab. We'll talk more about that later. I'm still working on giving you a quiz. I'm thinking maybe on Tuesday. So anyway, I'll figure it out today, and I will give you more details later. All right, that's it for now, and I hope you're having a good weekend. Okay, bye-bye.